It's going to be a little bit interesting. Our focus is going to be right here on GCF and LCM. Who knows what GCF and LCM stand for?
Greatest common factor and least common factor.
Awesome. Greatest common factor and least common multiple. Why are we doing it? To determine commonalities between numbers. This will help you, especially with addition and subtraction of fractions, as well as several other things. These are critical math concepts to understand. A lot of kids really struggling today with, I know I got it if, I understand the cake. You will hopefully understand it by the end. If you don't, we need to talk about it. Really important that you guys understand the cake method because it makes this whole process so much easier. Slight change. Your homework is actually set number 4 on page 90. I haven't changed it on the main board yet. So for those of you that really do use your agendas, you can make this page 90, set number 4. Okay? You didn't make a mistake because I didn't put it up there. That was actually Miss Witt pointing out that it is probably a little misleading. You'll see when we get to it, page 91 basically says, for the problem set, do anything we haven't done, and we're using the exact same set. So, yes, there are 2 pages to it. Now, the first part of our lesson is actually kind of elementary. However, I find this to actually be really intriguing and interesting because it helps you understand why these things happen. So we're going to go through some real quick elementary stuff, and then we'll get into a little more depth about why these things are happening. Our first question, go ahead and open up to page 74 in Module 2. Page 74 in Module 2, it's the start of Lesson 16 on even and odd numbers. Okay, Sean, what is an even number? Divided into what? What into what? You keep saying it. What is it? Jasmine? Go ahead, Jasmine, you said it. So it'd be evenly divided by 2, okay? So an even number, any number that can be evenly divided by 2. Now there is another commonality to all even numbers. They end in what? 0, 2, 4, 6, or 8. So what are some examples of some even numbers? Luna, you got a question or? Go grab it real quick. You should bring that every class because most classes we do use it. Yes, Micah. Awesome, 1 million. Okay, what are some other even numbers? Mateo? 2? Let's get a couple more. 16? 4. So, the bottom line on this, doesn't matter how many digits the number has. No, it doesn't matter how many zeros are in the number. Doesn't matter what the number starts with. No, literally, the only thing that matters is what the last number is. Make sense? That defines an even number, okay? So, conversely, what is an odd number now? Jasmine? Okay, so can you tell me in words the opposite, any number that can be evenly divided by 2, what would be the opposite of that? No? Leslie? They cannot be divided evenly by 2. So any number that cannot be evenly divided by 2. Now there's another commonality in these numbers. They all end in what numbers? Good. 1, 3, 5, 7, and 9. So these are our odd numbers. Yes, Aaron? Like? Good. So an example, 9,999. Any other examples of odd numbers? Sean? Like what? 99? Adi? 5? See, one more. Nora? 61. So again, doesn't matter how many digits there are. How many nines or zeros there are in the number. What it starts with. Those are all irrelevant. Literally, the only thing that matters is what that last number is. Everybody good so far? Okay, our first thought question. What happens when we add two even numbers? Nora? Good. You actually even got into the next part we're going to do. So hopefully they heard that at home. So when it happens when we add two even numbers, they are even. The answer is even. And that is always. So it's always even. And in case they didn't hear it at home, what Nora said was numbers like 4 and 4, they're all set in pairs. So there's always going to be a set, and you don't have anything left over. So it will always be even. Good. Okay, let's turn the page. 75. So now we're going to work through a little bit of a process to help you understand why this happens. So why is the sum of two even numbers even? So let's think of the problem 12 plus 14. We're going to do some models to help you see what's happening. So we're going to model 12 and 14, and we're going to do this with dots lined up with each other. So for 12, I'm going to end up with 6 sets of dots. Plus, for 14, I'm going to have 7 sets of dots. And then in part B, the instructions are to now circle pairs of dots to determine if any are left over. So in the 6, if I circle the pairs, I end up with 6 sets of pairs, nothing left over. The 14, I have 7 sets of pairs, but there's still nothing left over, right? So this is what Nora was saying at the end. If I'm adding up even numbers, they're always going to have paired dots. So there will never be anything left over. Okay? So is this true every time two even numbers are added together? Why or why not? Yes. There will always be excuse me, matched pairs of dots. For both numbers. So hopefully with the models now, you guys can see and understand why it is that every time I add two even numbers, I get an even result. Because I'm adding even numbers, there's always going to be dots on top of each other every single time. Okay? Now, part 2, why is the sum of two odd numbers even? If I have two odd numbers, why is it that I get an even answer? So let's think again of a problem such as 11 plus 15. Let's draw dots to represent each number. So for the 11, I'm going to end up with 5 sets of dots. but with 1 left over, right? And then in the 15, I'm going to have 7 pairs of dots. But what else am I going to have? 1 left over. So our second part, we get circle pairs of dots. So for each pair, I'm going to go ahead and circle it. So I've got 1 there. I do all my pairs here. I've got 1 there. So guess what else I can do now? I can use that 1 from each set, and I can now make an additional pair of dots, can't I? First period, we were calling those bananas. Because we have pears and bananas. We were using fruit analogies. But does that make sense? So does it matter what size that odd number is? Will it always have 1 extra dot at the end? Yes. My second number, does it matter how big it is? Will it always have 1 dot at the end? Yes. So because I'm always going to have a dot at the end for both of those, that now allows me to make an additional pair, meaning that my result is even. So is this true every time? Yes. Each odd number will have 1 dot left that can be combined for another pair. So again, regardless of how big the number is, doesn't matter. The fact that it's odd means there's always going to be that 1 extra dot at the end. With each of those numbers having an extra dot, I can now combine those for a pair. Yes, Sylvia. I hadn't done that yet today. That is true, though. In this case, both answers are 26. And they are even. So whether it's an even plus an even or an odd plus an odd, my answer will be even. Does that make sense? Okay, let's turn the page. Now let's look at our third situation. Now, why is the sum of an even and an odd number odd? So let's look at 14 and 11. So we'll do the dots thing again to help us understand the even odd concept. So 14 is going to have 7 sets of dots. And then 11 is going to have 5 sets of dots. But 11 is going to have 1 left over. Okay? So again, let's circle pairs of dots to determine if anything's left over. So going through the 14, I've got 7 pairs of dots. Do I have anything left over? Nope. What about on the 11? I start circling these. I now have 5 pairs of dots. But what do I see? I have 1 loner. I have 1 cannon out here who's never going to have a partner. Sorry, Cannon. Now, will Cannon ever have a partner? Or is Cannon always going to be out here by himself? Okay? There's no one here for him to match up with, right? Ooh, okay. So, is this true every time I have an even and odd number?
How many people are here?
Yeah, because 1 is always going to match up all the way across, right? The other one is always going to have that 1 odd one left at the end. So yes, there will always be 1 dot left over. Now, interesting thought question. What if I reverse the numbers? What if I did 11 and 14? Is that going to make a difference? What property says that? Thank you, Nora. Great job finishing it. Commutative property of addition states that changing the order doesn't change the result. So regardless of which way I add them, it's still going to be odd. It just means that the one with the lone dot is now the first number instead of the second one. Yes? Commutative. Nope, there's no N. Commutative property. So let's sum up. What rules did we just determine? If I have an even and I add an even number to it, what do I get? What's my answer? Even, because everybody's matched up, right? If I have odd and I add an odd number, what happens? Still even, because even though they are each odd, they each have one by itself that can now form a new pair. But if I take an even plus an odd, what happens? It's going to be odd. We've always got that one poor lone dot that will always be by itself. Do these rules make sense? Do you understand why these rules are what they are now? Makes sense, right? Now let's take a look at our next operation. What if we look at products? So we're going to play a true-false game first. So I will warn you, pay close attention to the verbiage because that is important. The product means what, guys? Multiplication. Aaron, don't forget to put the pass back up and sign back in. The product of two even numbers is even. Is this true or false? Wow, Sylvia sounds really confident. Nora, you sure about that? Are those two even numbers? Okay, guys, I'm hearing a lot of debate. Let's raise our hands. How many of you think this is true, that if I multiply an even number times an even number, I get an even result? Hands down, how many of you think that's false? That if I do even times even, I get odd? Okay, why do I have so many that didn't vote? You only have two options here. Hurry up, Drosimos. Okay, let's try this again. Everybody needs to vote. If you do even times even, is it even? Raise your hand if you think it is even. Kaylee, your hand up or not? Okay, hands down. How many think that even times even could produce an odd result? Okay, so we're going to call this one true. Our next one, the product of two odd numbers is odd. How many think that one is true? Two odd numbers is odd. Guys. Okay, quiet down. Let's take a vote on this one because I'm hearing a lot of debate. How many think the product of two odd numbers is odd is true? How many think that is a true statement? Okay, hands down. Hands down. How many think that a product of an odd number, two odd numbers is false? That you can actually get an even result. Okay, we've got some debate on this one. I'm going to leave this one up. Okay, now let's look at our third one. Product of an even number and an odd number is even. How many think this one is true? Even and an odd is even. You think that's true, Micah? What did you just say? Okay, I thought you said 3 times 3. So guys, is this one true? Raise your hand. We're multiplying. No, product means multiply. So is your hand down now? Part C, number 6. Okay, hands down. How many think that one is false? Okay, so you guys seem pretty sure on that one. So we'll call that one true. So the only one we have really debate on is our second one. Let's look at our examples to try to figure this out. So we'll use some numbers like a lot of you were doing. I really like the way you guys jumped into some examples to help you think through whether it was true or not. So let's use 2 smaller numbers because I want to model this. So what are 2 small, different, even numbers that we could use? Lysena? 2 even numbers. Let's use different numbers, though, because the modeling gets otherwise 2 times 4. Okay, I like that one. Now, interesting thought. What does multiplication mean? But what does it mean? Repeated addition. So if I say 2 times 4, what am I really saying?
4 2 times. No. No, you have 4. You put 1 up.
Nora? I don't like the way you're saying it. I like to say it this way. So the way to think of this is the first tells me how many groups I've got. My second number tells me what number I have groups of. So this is saying 2 groups of 4. So it's what Madison was saying. I just didn't like the way she was saying it. So we're saying I'm adding 2 groups of 4. So if I put this together, 2 groups of 4, and then I do my dots analysis, what do we see? Do I have anything left over? Nope. Will I ever have anything left over? No. So from a modeling perspective, let's look at it the other way. What if I did 4 times 2? Does my model look different? Yes, it should. Now I'm talking about 4 groups of 2. So this one looks like, okay, if I circle my dots, has my answer changed? No. Commutative property of multiplication tells you the answer is no different, but my model does look different. I'm doing something different in 2 times 4 versus 4 times 2, aren't I? Okay? Now let's look at the one where we had some debate on. The product of 2 odd numbers is odd. Some of you thought this is true, some thought it was false. So let's look at some examples. Mateo? Let's do different ones so I can actually see the difference in the models. Emily? I like that. Okay, we'll go with that. So 3 times 5. So that means I've got 3 groups of 5. So 1, 2, 3. And if I start circling my pairs, I have 1, 2, 3, 4. I have 6 pairs. But then I've got these 2 loners, these 2 lone cannons out here. But I can now put them together and make them a pair. So there is hope for you. But unfortunately, I still have a loner, don't I? Is this always going to be the case? Guys, will this always be the case?
No.
Why not? Okay, if I did times 9, what would happen?
Sometimes it would give you an odd and sometimes it would give you
Why?
No.
If I did 9 times another odd number, what's going to happen? It's always going to be odd, because if I've got an even number of an odd number, there's always going to be 1 left over at the end, right? Or an odd number of an odd number, sorry. There's always going to be 1 left, because most of them will match up. So if I did, for example, 5 9s, 4 of them are all going to match up, but that 5th set is going to be by himself. Make sense? So yes, this is always true, guys. So you can add a true to this statement as well. And then our last one. Hey guys, stop the chatter, guys. Getting a little loud. So now our last one. Product of an even and an odd, Micah. Product of an even and odd is even. This one is interesting. I'm actually happy to see you guys all said true. So let's use an even and an odd example. Cannon. Multiplying, yes. So 2 different numbers, 1 even, 1 odd. 3, okay? So this is saying 2 groups of 3. So I have 1 group of 3, a second group of 3. I start doing my dots analysis and pairing them up. And what do I notice? They each have 1 left over that makes another pair. So can you see why it is even? Okay? Because if I'm doing an even number of a odd grouping, they're always going to have a pair to match up with. What if I reverse it, though? What if I did 3 times 2? Not the exact, my model looks different, right? Because now they're all matched up evenly on the pairs. Because back to our first one, does it matter how many even numbers I add up? Will I ever have an odd answer? No. So does this make sense now? Okay. Let's turn the page. Here we have actually written the rules out for you. So they are different. Kendall. Guys, quiet down, please. Zuriel. We've done it in 2 different categories because the rules do change based on the operation. In adding to even numbers is even, that does work as well for multiplying. However, for adding to odd numbers is even, the product of 2 odd numbers is odd. It's changed. In adding, even and an odd is odd. In multiplying, even and an odd is even. So you have to think about what you're doing. Why do I point this out? If you mark the text on your directions, you're going to see a couple very important things. First is, what does it say? That's solving. So do I expect to see an entire piece of paper with all of these problems worked out? No. If you do that, it's actually wrong, because you're not supposed to do that. We're wanting you to use these facts we just learned to analyze the numbers, not give us an answer. Okay? But there's this very critical second part to our instructions here, isn't there? Explain your reasoning. No. But I will make it easy for you. Guess what, guys? Right here are your explanations. Yes, this is homework. This is page 78. Yes, Micah? Correct. So since this one's on the video, I'll actually do the first one for you. In this case, my answer, I'm adding an even and an odd. So what's my answer going to be? Odd. So I say it's odd, and then my reason is there will always be one dot left over. Or you could just say, in this case, the sum of an even and odd is odd. I would take either one of these. You don't have to write both of them. The first one explains why, because there's always one dot left over. The second one just gives the rule. I will take either one of those as your explanation. Any questions on this piece of the homework? Okay, the most difficult one here is part 5. I'll give you a hint. Do the first two, that gives you an answer. Then use that even or odd to do the next one, get an answer, and you just continue doing that till you get to the end of the string. Yep.
Okay.
Because you're adding, you're just looking at the last digits. Okay, let's turn to page 85. This is the start of lesson 18. So we're skipping lesson 17. This one is where we're going to get into LCM and GCF. Okay, Maddie, you ready? I got a big question for you. Which is going to give me a larger answer if I'm comparing two sets of numbers? Will my answer be larger for the greatest common factor or the least common multiple? Which one is larger, the greatest common factor or the least common multiple? So in a set of numbers, I compare the same set of numbers, my greatest common factor will be larger than my least common multiple, right? Does that make sense to everybody? Okay? Is there anybody that doesn't make sense to you? We're saying if I compare two sets of numbers, say 12 and 18, the least common multiple of 12 and 18 is going to be smaller than the greatest common factor. Does that make sense to everybody? Why not, Madison? Well, it doesn't matter. I just said least common factor or greatest, or least common multiple or greatest common factor. Ironically, believe it or not, guys, she's the only one that's going down the right path. You guys are all focused on least and greatest, which is very misleading. The more important words are multiple and factor. What is a factor, Nora? The factors make the product, right? So factors are what numbers did I multiply to get that number. What's a multiple? Multiple is as I multiply a number out. So let me ask, no, it's perfect that you asked that. Guys, so let's refocus on this question. Which is going to give me a bigger result? The building blocks of a number or what I get as I multiply the numbers out? Wesley? As I multiply them out. So if you focused on the greatest and least, you're actually going to get the wrong answer. Because least common multiple is actually bigger than the greatest common factor. So we have our definitions here. They gave them to us. The greatest common factor of two whole numbers, both non-zero, is the greatest whole number that is a factor of each. So we're looking for the factors in this one. Least common multiple is the multiple of each number. That is the first multiple of each of the numbers. So I'm going to go through 3 different ways to show this. I'm going to show the 2 I don't like first, but then I'll show you the one that is going to be easiest. Okay? Our first way is the elementary school way, where I take my 2 numbers, 12 and 18, and I list out all of the factors for both numbers. So I'll give you a hint. Whenever you're doing a factors list, always start with 1 because every number is a multiple of 1. So 1 times what is 12? 12. 1 times the number is always itself. What's my second set of factors? 2 times 6. And I do them in order just to make it easy and keep track. What about 3? Will 3 go to 12? 3 times 4? Good job. So I can't do any more, so I'm done on that one. Now let's look at 18. Boys, you're supposed to be watching and writing, not whatever it is you're doing. Okay, 18. What's my first set of factors? 1 and 18. What's my second set?
2 and 9.
I actually go 2 and 9 next. And then 3 and 6. Okay? Is 4 a factor of 18? No, 5? Okay, now I'm at the 6, so I'd just be reversing my table so I know I'm done. So I now go through my factors and I circle all of them that are the same. So they both have a 1. They both have a 2. They both have a 3. They both have a 6. So for greatest common factor, I say which one of those is the biggest. So my GCF of 12 and 18 is 6, because that is the greatest common factor between them. Okay, now here is my biggest problem with this one. If I miss a set of factors, I may have missed my answer. Or if I write any of them down wrong, I may miss my answer. So let's look at a couple other ways to do this. The next way is what we call by prime factorization. In other words, I build a factor tree off of each of them. So I take 12 and 18, and I use one of the factors that is not the 1 to figure out what numbers I would multiply to get that. So what would I multiply to get 12?
6 and
2 and 6. I always list it from the small one to the big one, partially because every time I get to a prime number, I circle it. This branch is now dead. I can't go any lower than that. What about 6? Can I break it down further?
Yeah.
2 and 3. So if I can break it down further, I do so. That becomes 2 times 3. 2 is prime, 3 is prime. Once all of my branches are dead, I am done factoring that number. So to write out the prime factorization, I just write out every number in a circle with the multiplication between. So 2 times 2 times 3. That is the prime factorization for 12. Okay? Now I can do the same thing with 18. So what were the factors of 18 that we could use? 9 and 2. 2 and 9. Again, I personally list them smallest to largest because I like to end my trees and build it down. But technically, you can do it either way. There's nothing to multiply to get 9?
Yes, there is. 3 times 3.
3 times 3. Now that one's dead. So I rewrite this one as 2 times 3 times 3. So here is why I don't like prime factorization. And it's because it gets really confusing as to how I find GCF and LCM for these two numbers. So for GCF, what I have to do is I find the smallest number that they both have in common, and I multiply all of the smallest for each of the factors. So in other words, do they both have a 2? Yes. Do they both have 2 2s? No. So the greatest common factor is a 2. Do they both have a 3? Do they both have 2 3s? No. So the greatest common factor is they have 1. So 2 times 3 gives me 6. So that's my GCF. Okay? Here's why it gets confusing, though. Listen up. If I now want to find the LCM, the least common multiple, now I find the largest number for each factor. Okay? So this one has 2 2s, this one has 1 2. Which one's bigger? 2 2s. So 2 times 2. This one has 1 3, this one has 2 3s. Which one's bigger? 2 3s. So for the LCM, I now need to multiply all of this. So 2 times 2 is 4. 4 times 3 is 12. 12 times 3 is, okay? So my GCF, I go through that process. My LCM, I go through this process. It equals 36. Okay? Yes? You're going to miss a lot of important stuff, especially since you haven't even written any of this down. Drosimos. I mean, I've got a whole 2 factor trees with everything written down. You've done none of it. Yes? Well, this isn't actually the easy one. I've got a much easier way I'm about to show you. Because quite honestly, I don't mind the prime factor trees. This isn't bad because it comes down to your 4 key numbers, 2, 3, 5, 7. I just divide each factor until I get down to where I can't divide it by those. The hard part is remembering what do I pull out for GCF, what do I pull out for LCM, because it's a different set of numbers. The other one's going to make you feel even smarter, okay? But let's take a step back to elementary school again. Not kindergarten. Kindergarten wouldn't get this advanced. But here is your elementary way. Guys, quiet down. Here is your elementary method for finding the least common multiple. What I'll do is I take my number and I list the first 10 multiples of that number. Okay? So we're going to start with 12. So I start at 12. The next multiple, 12 times 2, is going to be 24, 36, 48, 60, 72, 84, 96, 108, 120. Now, some of you that are not quite as good at math or don't know your 12 factors would probably go considerably slower on this. Luna, make sure you write all these down. Everything I'm writing on the board should be in your book. Now, is it really fast to do this? I caution against that, because if you go really fast, there's a much greater chance you're going to make an error. I heard several that said yes, though. Okay? Now watch, this gets even more fun when we do 18. Because we have to do the same thing now for 18. So for 18, now I'm just adding 18 each time. So it's kind of like we were doing the division algorithm where I've got my table, but I'm just adding 18 mentally each time. So 18 plus 18 gives me 36. Now I'm adding 18 here, so that gives me 14. 4 and 1 is 5. 54. 4 and 2 is 12. So 5, 1 is 6 plus 1 is 7. 8 and 2 is 10. So 7, 1, 8 plus the 1 is the 9. 0 and 8 gives me an 8. 9 and 10, 108. 8 and 8 gives me 16. 1 and 1 is 2. 6 and 8 is 14. 2 and 1 is 3 plus the 1 is 4. 8 and 4 is 12. 4 and 1 is 5 for a 6. And 180. Okay, we'll finish this after lunch. Okay, just to finish off what we were just talking about. Hope you guys were able to get all the rest of those listed. I know I did it pretty quick right before lunch left, but our next step, once we have all of the factors, is to go through and circle the ones that they have in common. So what number did you guys notice was the same? Sean? 72, awesome. You saw that there is a 72 on both of them. Good, well done.
Yes, I have very good eyes.
Wesley? 36. Are there any others? Osana? 108. Are there any others?
No, wait. There isn't any others, but if we kept going, it would have been 144.
But we didn't. Yes, Madison? We already did 36. Yeah?
I heard you start talking, and I did not say 36.
The second person, Wesley, said 36. Okay, so here's the deal, guys. 2 reasons I don't like this method. Reason number 1, if I make one math error in either string of numbers, girls, please stop. One math error in either string of numbers, I could totally miss my LCM. The second thing, just like Sean, he has really good number sets. The first numbers he saw was 72. If you're doing a test and you're in a hurry and you don't take the time to really scrub the list and see that there was actually a 36, you would have gotten a common multiple, but you would have not gotten the least common multiple. Nora? Yeah, good. Just sign out. So our LCM for these two is 36. So we already showed you how to do that using the factor trees. So it took us close to 20 minutes to do all this, right? I will grant that was doing 2 different methods. Now, do you guys want to see the easy way to do this? Okay. This is what we call the cake method. The reason it's called the cake is just like a cake. It builds in layers. So in the cake method, all I do is I take my 2 numbers. In this case, it's 12 and 18. I write them side by side, and I build the first layer of my cake. And in my first layer of the cake, I focus on my 4 key numbers. What are my 4 key numbers?
3, 5, 9, 7.
So close. You missed one, though. 2, 3, 5, 7. So those of you that don't have that down yet, please write it down again. Cake method is designed around those 4 numbers. So all I do is I take a look at my 2 numbers, and I say, can I divide them both by 2?
Yes.
Yes. If I say yes, I put the number to the side, and then I just do the division. So 12 divided by 2 is 6. Now 18 divided by 2 is 9. Okay? I then check each level. This is why it's a cake. So I check 2 and 6 and 9. Can I divide those both by 2? No. It has to divide evenly. Can I divide them both by 3? Yes. If I say yes, I add another layer to my cake. Okay? If I have nothing but my prime numbers on top, I know I'm done, unless it's the same number, which in case I could pull it out. Now, here's why this is so awesome. Because you have now you not only have all the information greatest common factor, you also have all the information for least common multiple. The only thing that differs is what you are multiplying. Greatest common factor is the factor. So I'm going to multiply straight up the side. So it's kind of like an arrow. So whatever numbers are there, I multiply. 2 times 3 is 6. Least common multiple is multiplying everything. So kind of the M is everything on the outside. So I now multiply all of this. 2 times 3 is 6. 2 times 3 is 6 times 6 is. See how easy that is? Super, super easy. Let's look at a couple other examples, okay? So we'll do this first set here together, 30 and 50. So I write down the 30, the 50, and I put a division bar over both. What number goes into both of them? 10. Here's another advantage to the cake method. If I do prime factorization method, I have to break them all to their prime factors. If I use cake method and I see a larger number than 2, 3, 5, or 7, I can use it. So I can use 10, and now I say that is 3 and 5. So my greatest common factor is still on the side. The factor is always on the side because it's a smaller number. So that's going to be 10. My LCM, now another advantage, LCM, I can multiply in any order I want to, right? So for me, I'm going to make the math easy on myself. 5 times 3 is 15. 5 times 3? No, 5 times 3 is 15. 15 times 10 is? I mean, this took us, even with talking, what, about 45 seconds? Now, I'm just going to show you real quickly. Here's another reason I like this. If I didn't see the 10, watch what happens, guys. 30, 50. If I just start on my 4 key numbers, I say 2, okay? Divide those both by 2, 15 and 25. Those I can divide by 5, gets me 3 and 5. So I still multiply. 2 times 5 is 10. Yep. LCM is 150. So it doesn't matter which way you do it. If I see the bigger number, I can take it quicker. But either way, I will get to the correct answer as long as I don't make a math error. Does this make sense? Yes, Jasmine? Yeah, I multiplied everything on the outside. So 3 times 5 was 15, times 10 was 150. For multiple, I multiply everything on the outside.
I'm looking at the next page.
Okay? Let's look at our next one, 30 and 45. So 30 and 45, what will go into both? Can I divide them both by 2? No, by 3? By 5? Okay, someone said 5. So I put a 5 out here, it gives me a 6 and a 9. 6 and 9, what can I divide those by? 3. Gives me a 2 and a 3. So my GCF is just up the side. It's like the arrow. So I'm multiplying the side for GCF. 3 times 5 is 15. My LCM, the multiple again is everything on the outside. Now again, another big advantage of this, I'm multiplying all the numbers, commutative property of multiplication. I get to choose the order. So I'm going to make the order easy for myself. What's 5 times 2? 10. What's 3 times 3? 9 times 10 is? That's why I like this. It's very easy. So focus in on your 4 key numbers, 2, 3, 5, 7. If you see a bigger number, like for example, that I saw that I could do 15, you could have done it in 1 step. Good for you. You got it there 1 step quicker. Did it really make a big difference? No. And I'll be honest with you guys, sometimes there may be a bigger number you can do, but it's actually easier to use the smaller numbers and do multiple steps because the math is actually easier doing single digit division. Okay. That being said, we've got about 18 minutes left in class. I'm going to give you guys about 15 minutes to finish. Actually, we'll give you like 10 minutes to finish the next 3 sets. So find the GCF and LCM for the next 3 sets of numbers. Sorry. Guys, listen up. I was helping people and time got away from me a little bit, so we got down to 3 minutes. So please stop talking. Pay attention, because I'm going to fly through this. So just to show these last 3, hopefully you've got the answers. 45, 60, I can do 15 into both. Gets me a 3 and a 4. My GCF is always on the left side, so it's 15. My LCM, I go all the way around. 15 times 4 is 60, times 3 is 180. 42 and 70. I can divide both those by 7, gets me a 6 and a 10. Divide those by 2, gets me a 3 and a 5. Excuse me, GCF is 14, 7 times 2. LCM, 2 times 5 is 10, 7 times 3 is 21, gives me 210. Last one, 96 and 144. This one, 48 goes into both, so that's going to be 2 and 3. My GCF is 48. My LCM, 48, 96 times 3 is 288. Okay, so here's the reason I had to rush through this. Some of you in your paper, in your agendas, wrote down that the homework is page 91. Page 91, the problem set says complete the remaining stations. Those of you that paid attention and rewrote it after I changed it on the board or from my board, you realize what you have to do is find the GCF and LCM for the numbers that are listed in station 4. Okay? So ignore the plus signs, those don't matter. All you're doing is using these 2 numbers. So for number 1, I find GCF and LCM for 1218. Does that make sense? For number 2, I'm finding the GCF and LCM for 42 and 14. Questions? Okay, good luck. Enjoy your long weekend, guys.